Good afternoon, everyone, once again. Can I ask Reverend Tony Allen to speak, to come, please?
Good afternoon, everyone. May we stand, please, for prayer? Let us pray. Our Father and our God, we come to you this afternoon and we are thankful that, Lord, you have watched over our lives throughout the past hours of the day. Thank you that you have taken us to our jobs and we executed our task so that here we find ourselves in this conference room, oh God, for this presentation, Math Talk. Lord, we know that this is a subject with which many persons have had challenges. Lord, through our systems, our education systems, whether it's at the primary or the secondary levels, there's still a lot of room for improvement. So we come today into this discussion and we are hoping, Lord, that ideas would be fruitful, that something that would be said and done by our presenter, Dr. Sami, Lord, would cause our minds to become enlightened to other strategies and methods of teaching math so that, Lord, we can have greater results here in our nation of Montserrat. We pray, Lord, if there's need for resetting and retooling, Lord, that today would be the beginning of the end of, oh God, poor levels and poor performances in the math, in the subject math. So we commit this afternoon's discussion into your hands, and we thank you that it will be fruitful and beneficial to not just those of us who are here, but, Lord, to those who may be listening and the wider community of Montserrat at large. So we thank and praise you now in Jesus' name. Amen. Thank you very much. You may be seated.
Her Excellency, the Governor, Mrs. Sarah Tucker, and Mr. Tucker, Premier and Minister of Finance and Economic Management, Honourable Joseph E. Farrell, Deputy Premier and Minister of Education, Works, Labour and Energy, Dr. Honourable Samuel Joseph, Minister of Education, Health, Social Services, Sports, Youth and Ecclesiastical Affairs, Honourable Charles Kernan, Minister of Agriculture, Lands, Housing and the Environment, Honourable Cranston C. Buffon, Parliamentary Secretary, Health, Social Services, Youth and Sports, Honourable Veronica Dorset Hector, Honourable Speaker of the House, Ms. Charlena White, Permanent Secretaries, Directors, Principals, other governments, teachers, youth parliamentarians, attendees, members of the media, viewers online. We are thrilled to extend a warm welcome to all of you for joining us today for the Math Talk, where we celebrate the fascinating world of mathematics. Today's event forms part of the National STEM Week of activities. The week, taken from the 22nd to the 26th of April, is a collaborative effort between the Ministry of Communication, Work, Labour and Energy, the Montserrat Volcano Observatory, and the Ministry of Education, Youth Affairs and Sports. The week brings together educators, industry leaders, policymakers, and the community members to champion the importance of STEM education and inspire the next generation of innovators, and problem solvers. STEM weeks serve as a platform to showcase the possibilities of STEM fields through interactive workshops, engaging presentations, hands-on demonstrations, and collaborative projects. Participants are exposed to the excitement and the relevance of STEM in their daily lives. It fosters inclusivity and diversity within STEM disciplines, ensuring that opportunities are accessible to individuals from all backgrounds, our students, and the community alike. The impact of initiatives like STEM Week extend far beyond a single event or a week. By sparking curiosity, nurturing talent, and fostering culture of lifelong learning, we laid the foundation for a future where STEM education serves for a positive change and sustainable development right here in Montserrat. And with that, I say welcome. Welcome to today's Math Talk, where we embark on a journey to explore the fundamental question: what is math, and do we teach it? This seemingly simple inquiry holds profound implications for education and our understanding of the subject as a society. I would like to invite the moderator for today's talk, Ms. Shial Chapin, ICT Officer within the Ministry of Communications, Work, Labor, and Energy. Please join me in welcoming Ms. Payne, our moderator for today's discussion.
Thank you. Good afternoon, everyone, and welcome to today's Math Talk. As we gather here during STEM Week, we are reminded of the immense importance of STEM education in our rapidly changing world. STEM, which stands for Science, Technology, Engineering, and Mathematics, is the cornerstone of innovation and progress across various fields, from healthcare to sustainable energy, agriculture, and even the fascinating realm of artificial intelligence as we know it today. However, while STEM receives much attention, there's often a gap when it comes to the mathematics aspect. Today's event aims to address this gap by focusing on the pivotal role in mathematics in shaping our future. Mathematics, often referred to as math for short, goes beyond numbers and formulas. It's the language of the universe. It touches every aspect of our lives, from nature to technology, from arts to economics. Today's event aims to address this gap. At its heart, maths is about reasoning, problem solving, and abstraction. It's a universal language that transcends cultural boundaries. Today's Math Talk, where we embrace on a journey to explore the topic, what is math, and do we teach it? This seemingly simple inquiry holds implication for education and our understanding of the subject as a whole and as a society. Are we teaching math effectively? That's the question we're here today to explore. We believe that math education should encourage curiosity, creativity, and critical thinking. It's not just about memorizing rules. It's about engaging exploration and discovery. We must cultivate a growth mindset in mathematics where mistakes are seen as opportunities for learning and growth. How do we empower students to tackle challenges with confidence and determination? Together, let's reimagine math education and inspire the next generation of innovators. Let's continue this conversation beyond today's event, embracing curiosity and diverse perspectives. Thank you all for being here, and now, without further ado, let me introduce our presenter for today's Math Talk. Educated at the University of the West Indies, UWI, and Baylor University in Texas, Dr. Joseph holds a PhD in physics, a master's in computational physics, and first-class honors in mathematics. He was one of the 10 students accepted into the High Energy Physics Postgraduate Diploma Program at the prestigious ICTP institution in Istria, Italy. I hope I pronounced that right. Dr. Joseph returned to Montserrat in 2010 as an educator at the Montserrat Secondary School and the Montserrat Community College. Believing that Montserratians should leverage their ICT skills to draw businesses from the global community, Dr. Joseph, along with his brother, Dr. Daniel Joseph, and Manish Felicia, established Montserrat's first software company, LavaBits. LavaBits has produced various apps and software currently in use by the government of Montserrat and the Financial Services Commission. Montserrat is now part of a global world connected through technology. Its future depends on its ability to exploit its geothermal energy and ICTs. and motivate and make use of its young people and human capital. These are all issues Dr. Joseph has invested energies and experience towards and has had tremendous success. Dr. Joseph is also a member of Parliament. After being elected in 2017, he is now Deputy Premier and the Minister of Communication, Works, Labour and Energy. Ladies and gentlemen, I present our presenter for this afternoon, Dr. the Honourable Samuel Joseph.
Good afternoon. After you hear this kind of introduction, sometimes I sit down and I wonder, where am I going to put myself to the stress that's going to happen later down this week? But moving on. So we're here to do the math talk, and I heard the prayer by Brother Tony and the introduction by Miss, remind me again, Annalisa Taylor and Miss Shelsha here, with the expectation that I'm here to provide answers and various such things. But this will be one of your disappointments tonight. I'm here to provide questions. If at the end you don't have more questions than answers, then I would have failed in my presentation. So I expect at the end of my presentation, there'll be more answers to be asked than questions to be asked than answers received. Because as was pointed out by the presenter, one of the purposes of math and to STEM is to spark curiosity and to produce in people the love of lifelong learning. So I'm continuing from what I said, that you would think that the purpose of mathematics education, the purpose of education in general, is to spark curiosity and not for a teacher to give you answers. So it's a curious topic, and you might be wondering, why did I choose a topic? What is math? Because it's obvious what math is. It's numbers and that stuff that we did in school that you don't use anymore. And do we teach it? And it's like, obviously we taught it. I spent 11 years being tortured by the subject, so I would hope that it was taught. But I learned something is different, but I would hope that we teach it. And governments expend millions and hundreds of thousands of dollars hiring teachers, building schools, saying that they're teaching mathematics and they're doing all these things, and we take taxpayer money and we argue that this is something that people should know. These are information that we think our students or young people should know. We expend tremendous energy in teaching mathematics. We teach something and we call it mathematics. So my question is, what is it? What is this math that we teach, and do we actually teach it? And if you all know me, you all will know the answer. So you ask somebody, what is math? If you do a curious experiment, it's not something for anybody to feel ashamed, but it's an interesting experiment. If I currently take last year's CXC exam, wherever the exam was in mathematics, and I give to everybody in the civil service, and I ask them to sit the exam, and we mark it, how many of the current people will pass? And I'm going to bet money, it's not to be embarrassment, that most people, if not all, except the teachers that sit in the room and teach math, will fail. And that everybody else will fail that exam. And that should start us asking ourselves certain questions. Because to get a job in most places and in our government system in Montserrat and across the Caribbean, you require that people have this subject you call mathematics with the argument that they need it for their job. So either one or two things or a combination of things are true. Either you did not need it or you're not doing your job effectively. So you get to choose. I won't choose for you. But or a combination of both, because we are requiring it, and I guarantee you that if I was to take that exam, repeat it across Antigua, Barbados, across the Caribbean, to people who are already in the system that said they require it, they will fail. But we're going to have our children doing it. We're going to pay tremendous money to send them to extra classes, stop them from playing their football and the video game. You must learn this math. It's important. One day you're going to need it. And they can't watch TV. They must go to these extra classes on Saturday when they could be playing with their friends. And we're going to insist that they get it. They're going to come to our places and ask for jobs. And we're going to say, you can't have it because you don't have this subject called mathematics. But the people who are currently in the system cannot do the exact same thing where you're asking people to come into the system to do. So it's either one, it's not necessary what we're asking for, or it was necessary, but the people in the system are not performing adequately, and we have people in charge of the civil service. They'll choose how they answer. That one I won't answer for them. So the question is, what exactly is mathematics, and why are we teaching it, and what exactly are we wasting so much human capital trying to achieve? And then I came in here, my good friend Howard was pointing out some of these formulas, and he learned them in school through much duress, and he had to learn when he put them back on exam, and he still knows them, and after 40 years, he has never used it. So if we look throughout the Caribbean, these are the pass marks for various subjects for last year, and mathematics is at the bottom in more ways than one. So then you said there is a problem. So now my job is to create controversy, as I said. And you ask, what is the problem? You say, well, only less than half the people pass mathematics. And in all the other subjects, it appears that more than half have passed or has passed. And so the numbers are there and the numbers say what they are. But the first statement I'm going to make that these numbers are lying to you. Because we require every child in our top forms to sit the math. The people that sit the French and the biology and so, they're chosen to sit it. So it is easy to watch numbers and say that we're doing math and we can interpret the numbers and this is what the numbers say. The numbers itself have no meaning. The numbers have meaning because we as human beings put meaning to them. And unless you understand the context, I'm going to come back to that later, unless you put back the context of where these numbers, these shapes that we call numbers come from, things are going to be confusing from the lower level, come all the way to the top. So we require every person in our system to sit mathematics, but not everybody does chemistry and biology. There are people that love the subject or want to be a doctor or have a motivation to do it. So we normally give this data and there's something is wrong. But what would happen if we require every single person to sit French or physics or principal accounts? I guarantee you will see a drop in the score. So first, so that's the first point here. When you look at information and numbers, they really have no meaning. It is us human beings who put a meaning behind the numbers, even from the very beginning. When we say 1, 2, 3, it is us, and I'm coming to that. So forget about all that. Point 2. Even that though, so we said 43% passed last year, and that was an increase on the previous year, which was 39%. I said that everybody is required to sit maths, but not everybody does. Because the people in lower forms and on the other, some of the other islands who have different schools, not everybody does. So less than half of your population of 16-year-olds, so CARICOM heads of education ministers and CARICOM heads have come together. We have come up with a mathematical syllabus and say our students at 16 should know this information. And at the end of 11 years of toil and labor, less than half know this information. So again, it's either we're telling them the wrong information or expectations is too high, or there's some other problem that we need to figure out what we are doing. So you have to go back to the beginning. The beginning didn't have numbers, we didn't have everything, and somebody walked along and they picked up one stone, and they have a stone. And then they walked along and they picked up another stone. And there's a conceptual leap that occurred. They did not say, I have one stone and I have another stone. They said they have two stones. And it seems trivial, but it's a huge conceptual leap. It is assigning a word to a quantity. It is deciding that this object here represents one, and when I have one here and another one here, they represent two. And if I add another one, I create another word, another symbol, and I call this three. It is a human abstraction where we have taken something from the natural world and given it a name. But there's something deeper. So we start off like that. And we said that we're going to, as we go back in history, the Egyptians, the different people, you eventually realize that they came up with systems of matching concrete physical objects in the real world with abstract names in their language and in abstract symbols to match what they say. Then they start to realize that certain patterns emerge. So if you go back 20,000 years in Egypt, you find these bone structures with these marks on it. But when you analyze it, you realize that they were dealing with prime numbers, which I'm going to come to. So back then, there was the concept of numbers called prime, which half the room is listening to know what I'm talking about, and half no idea what I'm talking about. But there was this concept of prime numbers at 20,000 years ago in Egypt that they realized that their patterns, so we came up with these abstract concepts to match things, but there were patterns in it. And there's something else deep in this story, because when we tell our story of monstrations and of black people, we tell is always the story of the Greeks and the Romans who do these things, and not about the Egyptians and the other people who had the same knowledge before. So we're very, very careful, as an aside, of the stories that we actually tell ourselves, because one of the stories, which is going to come out in my talk, that we tell ourselves that there's a certain people that can do math and a certain people can't do math, and the story you tell yourself affects how your character performs on the stage of life, and we have to remember that. So the different civilizations had ways of representing these things that we call numbers. How do you represent 1? How do you represent 2? How do you represent 3? How do you represent 4? And then they eventually realized that they ran out of fingers. They stopped at 10, and they didn't know what to do. So they end up with other ways of how they had to come up with other symbols. The kid didn't want to keep on inventing symbols. So the Romans and the other people had, okay, M would represent 1,000, C would represent 100, L would represent 50, so on. So you come up with symbols to represent these actual physical quantities. With the Mayans, you can see there's a pattern that they had to actually get it done. And there's another homework assignment. Actually, you can use your 10 fingers to represent numbers up to 1,024. You'll figure out how you can do that one. But it can be done. So it doesn't stop at 10, you stop at 1,024. So what they realize, on the right, we have real physical objects, and on the left, I have symbols. They're just symbols. So when we say that, what are letters doing in math, or we should be about numbers, the numbers themselves are exactly the same as the letters. They're just symbols that we use to represent something. So we have the symbol 1, which represents that one object. We have the symbol 2 that represent 2 fishes, etc. 3 that represent 3 apples, 3. And 4 that represent 4 stars. Those symbols, conceptually, are no different than if I use X or Y or A or B or anything I choose to represent something. It's just a representation of something. There's something conceptually deep about it that you could match objects to symbols. But if you start off by separating in math, there are special symbols, and these are the ones that we use for math. And there's other things that we use for algebra and whatever we choose to do. There's some exotic thing, and why we're doing these things, you have already created a barrier. But if you understand from the get-go that all we have done, and all the child had done when he took up the rock, is to associate a word to something. So we have to get that first. Then they realized that, we could put things together. So if I had 4 bananas, and I have 6 apples, they realize you can actually put them together, and if they go back and do their counting, they realize they get back one of their symbols called 10. So you're just playing around, and as a child, which all children would do, if you give them 10 blocks, they realize no matter how they separate the blocks, there are different combinations they can use to get back to the same 10. And we wanted to invent a word for that, because we didn't want to say putting apples and bananas together. So we invent another symbol, since we're lazy, and we call it plus, the addition. So we invent the plus sign, and we claim that is the way that to just represent in a conceptual way, when we put one set of objects to another set of objects, you'll get back something else. And then something curious you'll realize by playing around. If I take the 6 and put 4 to it, it's the same. If I start with the 4 and I put the 6 to it, I'll get the same answer. And because we want to sound smart, we invent fancy words, and we say that addition is cumulative under addition. In other words, it doesn't matter how you add, you get the same answer. There's no reason for this to be true. It seems obvious, but there's no reason for it to be true that if I do an operation in one order and do it in the other order, that I'll get the same answer. And you could check it by checking a book or something and say you turn left, and then you turn back to your right, and then try back and see if it first turn right, and if you turn left, the book is not going to face the same direction. You're going to get that it's going to face someplace differently. So this is not obvious that if I just repeat the order in how I get things, I get back the same answer. But it seems to be true when we invent this stuff called numbers, that it doesn't matter the order I place them in, I get back the same answer. So like, good, we have finished mathematics, we have solved, we have objects, we have names for all our objects, we know how to combine our objects, we can all go home, we can all get our O-level, and that's all in the first page of the syllabus, and we go home and we enjoy our holiday. But then, there's a curious thing that occurred when they realized, but we don't have a name for nothing. And that, again, that seemed obvious to you, because when you start school, you do 0. It took thousands of years before the Indians and other people realized that you needed a symbol to represent nothing. And there was a whole philosophical debate. Nothing is nothing, so you can't have something represent nothing. So the idea of 0 makes no sense. And there was long arguments about should you actually have a symbol which is something to represent nothing. Because nothing is nothing and nothing can represent nothing. And so there's a whole long philosophical debate about how that should be done. But eventually they agreed you need something to represent nothing. And we call it 0 in our system. So we now have a 0, so you add another page to your syllabus. You now need to teach the children about 0. If you have 6 things and take away the other 6 things, you will now have 0 of those things. So we're good. So we invent a whole number line with the first set start from 1 going all the way up, which you're going to come to. And then call those the natural numbers, because they say natural is what comes out of the natural world. We didn't invent them. We deduced it from the natural world. And then somebody added 0, and you're like, okay, we now call all these the whole numbers. So we're good. We've added another page to our syllabus, and like we are good now, we can deal with everything. But then you realize, suppose I now start with something, and I don't want to add or put something to it, I want to make it less. So I had 10 sheep, you wanted 2. So I gave it the 2 sheep. How do I deal with, I guess that's 8. How do I deal? I now have 8 sheep. So we invent another symbol, and we call it minus. And we say that it's going to be used when we take or remove from the original set that we have, and we call it minus. I'm like, okay, so we can now put things together, and we can now take it back, and we get back, we start with whole numbers and natural numbers, and you're going to get back whole numbers and natural numbers. Surely, we can all go home, talk is over, there's nothing else to do. That's it. But we all know that's not the case. So something interesting occurs. So when we did the plus, we say when we take the 6, and we put the 4, we get another number. And we take the 4, and we put the plus between, and we put the other 6, we get the same number. So you start with 11, and you took out 8, and you get 3. So some clever person say, okay, let's switch it around. So you start with the 3, the 8, and you say, I want to take 11 from that. And a big argument ensued. Obviously, if you have 8 things, you can't take 11 things from it. That makes no sense. Why are we even discussing that? You need to go back and read whatever Latin book you used to read back in the day, whatever they used to do back in the day, go plow your ground. You're just wasting time. This direction makes sense. This doesn't make any sense. Mathematics is over, we're good. But you start to realize it's not really true. So I start from this height, and I go up 5. I start here 0, and I go up 1 length, 2 length, 3 length, 4 length. What if I go this direction? how do I represent that? If you have money, you work for your money, the government tax it and take away all the things that are now left back with zero, and you borrow money from somebody and you now owe them. How do you represent that symbolically? So eventually the argument was settled and they decided we're going to move the numbers, not just go in that direction, we're going to allow the numbers to go the other direction and we're going to call them negative numbers. So we invented, so I'm using that word because it's going to have a discussion at the end. So we invented negative numbers. And we're now claiming that we're going to go positive numbers, we're going to go that direction, which already poses a problem because where does the end? And we're going to go the negative numbers, we're going to go this direction, and everything will work. So if I owe $5, I have negative 5 money. If somebody gives me 10, it means I now have $5. So I keep jumping. If I start from the left, when I add, I claim I go to the right, and when I subtract, I claim I go to the left, and everything works. If I add numbers, I get back another number. If I subtract numbers, I get back another number. It doesn't matter which order I do them, I will always get back another number. And we have negative numbers, and we have positive numbers, and we are now at grade 2. So which took thousands of years to do. So we're asking grade 2 children to understand things that took thousands of years for people to conceptually come to. And we are saying that if we just tell them it, that they should get it immediately because it's obvious. When it took the smartest people of this earth years to even reach to this stage. But we expect the primary school children to instantly grasp this concept without going through what I just did. Because we can just tell them these are negative numbers and you go this way and you go that way. And it should make sense to them when it did not make sense to even the clever people back then. Maybe they weren't so clever, but this is where we are. So we're like, okay, we are good. We have 0, we have natural numbers, you combine them, you get whole numbers, you combine them with the whole numbers, you get negative numbers, and we're going to call all of those things integers. So we invent a name to represent when you go from 0 that way, and when you go from 0 that way, and we're going to call all of those numbers integers, and we think that we have finished it. That is math. We are good to go. Time to go home. Now, what they also realized back then, you can start combining things, you can start asking questions. If I have 6 things, and somebody gave me a certain number, and I now have 10 things, how much did the person give me? You can ask, it's a legitimate question to ask. I had 6 things. Somebody gave me, I don't know, but somebody gave me something. But when I counted it, I now have 10 things. How much did the person give me? Well, I really expected an answer. The person gave you 4 things. So they realized you could write down these things. You could say that you don't know what it is, so you could invent a letter. Just like how we invent symbols for the things, you could invent a symbol. So you had 6 things plus box things equal 10. And you realize that there's mechanisms that I could figure out what goes here. And it came up with the concept of an equation. So it must balance because I'm saying that what I started here and put here is exactly equal to something here. So it's balanced. So if I have 5 kilograms on that side and 2 kilograms on that side, it balances with the 4 and the 3 on the other side. So if I remove the 3 on the right-hand side, what do I have to do on the left-hand side? You would have to remove the 3. So I'm now going to set things and I expect you to start conceptualizing it because I don't have the slide on purpose. So if I have 6 things plus box things equal 10 things, and I want the box, what do I have to remove on the left-hand side? You have to remove the 6. But if I remove the 6 on the left-hand side, I've disturbed the balance of the force, and I now need to, you have to remove it on the other side, but there's a 10 on the other side. So I remove the 10 on the other side, and I take 6 from it. Most people realize that you end up with 4. So box equals 4. But that is what you do because you've invented something called an equal sign, and you have balanced things. So if you do something on one side, you must do the same on the other side. But you have your syllabus to complete, and you have a test to do, and you don't have time to explain that to any child, so you tell them, take the 6 on the other side and change the sign. So it's on this side, all I want you to do, take it on the other side and change the sign. So we start inventing shortcuts to solve the problem without understanding why the math of it. Because what you're doing there, solving a problem, it is not math. That's using math to do something. The math is that the thing is balanced, and I want to rebalance it back. That is the math. Trying to solve that is accounting and something else that they're using math for. It's not the same as the math. So if you're teaching math, you're teaching that you're trying to balance the equation and not these tricks that keep adding up. Because it will fail you when we start to go on to the other, this is going to get more and more complicated. And you're going to realize you start following these rules, it fails. And the child and the adult is going to be confused. Why didn't it work when this is the rule? Because that's not the rule. That's a shortcut you use in this specific situation to solve that. So we must stop telling our children carry things on the other side and change the sign. So we invent fancy names, but we're balancing the left-hand side with the right-hand side. That's all we're doing. Whether we use X or Y or box or smiley face or book, it doesn't matter. They're symbols that we're trying to find out what they are. And all that we're saying, if you do something on one side and there's an equal sign, you do it on the other side and we are good. And there's something that always irks me, which I need to say now, because you will see things like in book 6 plus 2 equal 8 minus 4 equal 4. And that's complete nonsense. Because you're saying 6 plus 2 equal 4. Equal means that this here is exactly equal to the other side. It doesn't mean the problem continues after the sign. It does not mean, therefore, we can now do this. It means equal. Anyway, so we invent all these wonderful terms, and then using our integers that we just invented, because we're mathematicians and we're clever, we can now solve any problem like this. But then you realize, but no, you can't. Because when I take the 9 from the left-hand side, and I take the 9 from the right-hand side, I get 24 minus 9, which is 15, which is 24 minus 10 plus 1. So it's 15. And then you have 5, and then you have 5 of something, and you realize that the plus and the minus can't help you. You need something else. And then that something else, since we realize, so you're adding, and I'm telling you to do 6 groups of 4, which means if you go back to our number line, we're jumping 6 times, 4 times, and you're getting 24. Or you could count in 4s. You could go 4, 8, 6 times, you're going to get 24. Or you could add 4 6 times, and you're going to get 24. You could draw equal groups of 4, you're going to get 24. You draw a picture, and the last one is the important one, that I can make 6 groups of 4. If you play around and you say, instead of repeated addition, because I'm lazy, I don't want 4 plus 4 plus 4 6 times, so I'm going to call it, I'm doing it 6 times, so I'm going to obviously invent something called times. So I'm going to say we now have times. So instead of saying 4 plus 6 6 times, I'm going to say 4 times 6. And you invent a new operator, a new thing called multiplication, since times is too small. And if you want to seem clever, you have to use big fancy words. So we say multiplication instead of times. So we have something called times. So we've now invented something completely new. And then you realize something interesting on the bottom right, that the 6 groups of 4 is the same as the 4 groups of 6. And if you take a child and they play around with it enough, and they start with 12, they realize there are different ways they could arrange the 12, but it's still 12. 2, 6, 3, 4, 4, 3, 12, 1, 1, 12. There are different ways you could arrange it, and you're getting back to the 12. And then you're going to eventually realize the order in which I do multiplication doesn't matter, just like addition. So you're going to realize if you do multiplication on, so again, we use this fancy C word that we use, that multiplication is cumulative under the integers, wherever. So the order doesn't matter for multiplication, so you now find a short way of doing addition, and we're going to call it multiplication, and the order doesn't matter. If I multiply 2 integers, I'm getting back a integer. If I add two integers, I'm getting back an integer. If I subtract integers, I'm getting back an integer. But then I realized plus has a reverse process. So the obvious question was the reverse process of multiplication. So we need to, you need to know go the other way, and we say we're going to divide. So we invent another thing called divide. You have a pizza. It could have 6 pieces, and we could divide it up into a pizza. We have 6 people to share it to. You could divide it up into, you have 5 people that you want to share it to, and you could divide it up into groups of 5, and you say you're doing division, and you're saying how you're going to share it out, and you realize that you have something called division, which takes you back the other direction, but then you're going to realize something interesting occurs. If I try to I have 10 things, and I try to divide it by 2, I get 5. If I have 50 things, and I try to divide it by, let me do something I make sure I could do. No, not a bad number. If I have 60 things, and I want to divide it by 12, that's the number of hours in a thing you should work out. And I want to divide it by 12, I get 5. You get back in your thing called integers. The numbers that you start with, when I do divide, I seem to be getting back into them. But then, if you have 2 things, can you divide it into 5? What does that mean? And if I have 20 things and I want to divide it into 6, you realize you have a problem. You can't get back into your integers. You seem to be going someplace else. The numbers that you have doesn't seem to, and obviously in reality, if I have a pizza, I could cut it in half. So the system I've invented doesn't seem to encapsulate all the things I could do in the physical world. So clearly, the numbers that I'm using so far are lacking something. So we invent fractions, which when the fun starts in grade 3. And then we realize that we can write our fractions in a notation, or in a notation called decimals. So just like how we write out our numbers 1, 2, 3, you realize you could invent a point, and the things after the point go there. So you go tens, hundreds, thousands, and you go tenths, hundreds, thousands, and you go back the other way. So you just invent these things, and then you realize I could take a fraction like a half, which is following the rules I've invented. There's a 5 in the tenths place, so it's 5 over 10. And if I have 10 things and I take 5, it's the same as a half. So they're equal. So I realized I could now match back my fractions to my decimals, and then we call this, since we fancy and we don't want to use the word decimal, we say we have real numbers. And like you're good. I could add, multiply, subtract, divide, and real numbers with this decimal point is going to encapsulate everything I could do once I have my calculator. I don't need to worry about everything. I've solved everything in number theory, and I think that starts in grade 3, 4. We're now at grade 4. That we could do all of that stuff, and we could do everything go the other way. So then we get a new number line, we start at 0, and we invent things in between the integers. So between 0 and 1, we could have 0.8, you could have 2.2. You could go the other way, you have minus 3 over 2, minus 2.5. You have a symbol there called pi, and you have square root of 2. I'm going to come to these numbers, and a number e, and you could fit them into your real line, and you've invented real numbers, and you're like, I'm good, I've solved math, any number, any calculation you do, I'm going to come back to real numbers, and if you're fancy, you say the operations of addition, subtraction, multiplication, and division is closed on the real numbers. In other words, you will always get back a real number no matter what you do. You start there and do these operations, you will get back a real number and nothing else. So like, I'm good. But then you realize you could write an equation of this form. So I have something and I multiply it by itself, and we call it squared. And you subtract 2, and you get 0. And I want to balance it, so since I need to have a minus 2 on that side, so I need to add back a 2 on that side, which means I've added 2 on the right-hand side, and I get x squared equals 2. Squared is when you multiply something by itself, and the opposite is square root. So you're going to say that x is the square root of 2. And then you're going to ask the question now, can I write the square root of 2 as a decimal? Because there was the expectation at this time that every number I write down and any solution of the equation can eventually be written out it doesn't matter how far I go, I will eventually get it done. So can you write the square root of 2, which seems like a very simple number, as a decimal? And going back to my friend here, Howard, who do construction, there's a rule, and most of us have forgotten, so we're now going to secondary school, the Pythagoras theorem, which you forget. But it basically says, if you have a triangle, I'm going to call the sides A, B, and C, and you do a square on one side, and a square on the other side, and a square on the hypotenuse, and you add them up, you're going to always realize that when you add the A part and the B part squared, you're going to get back the C squared, always. And that took a long time to realize. The Greeks used it to construct their pyramids, because it tells you something else. If I have 3 numbers, so let's think about 3, 4, and 5. 3 squared is 9, and 4 squared is 16, and 9 plus 16 is 25. So the other side is 5. 5 times 5. So if you're doing construction, and you measure this to be 3 feet, and you measure this to be 4 feet, and you move your point until this is 5 feet, you know that this part is square. This will be, your building will be square. If you measure this 3 and this is 4, and you measure this and you don't get 5, tell yourself that you're not square on that side. But you could draw a triangle, and you could have one side 1, one side 1, which if you do the calculation, you get 1 squared plus 1 squared, which is easy. 1 times 1 is 1. 1 times 1 is 1, and 1 plus 1 is 2. That's easy enough. And then you now have to take the square root of 2. So the square root of 2 will exist as a physical length in the real world that we live. It's not an abstract thing. If I just draw a triangle on a paper, 1, 1, this side here is square root of 2. Can you write that as a decimal? So you have that, 1, 1, root 2. And the answer is you cannot. It goes on forever. It's going to be 1.41412, and it goes on forever. And then you have the real math question now. How do you know that it doesn't end? You're not going to sit down and do the calculation forever. So how do you know that you cannot write that as a decimal? And numbers get bigger and faster than we think. Because if I ask you if you're counting from 1 to 1 billion, so you're going 1, 2, 3, 4, and you're doing 1 every second, how long will it take you to count to 1 billion? So you have 1 billion seconds, and you have to do the calculation. It's going to take you 30 years. So if you're counting 1 to 1 billion, 1, 2, 3, 1 every second, it takes you 30 years. So when you hear people are billionaires, you start to understand the concept of where these numbers are just out there. So that number is far huger than we think. So obviously, you can't sit down and calculate that forever. So how do you know, because I'm making a statement that this cannot be written as a real number? How can you show that? That's your first homework assignment. Anyway, this part, the reason I'm doing this part is to try to explain what math is. This is the first part of my talk. So my statement is that this is what the math is. The math is asking the question, can this be written as a real number? And answering that question is the math. The techniques that come out of that we use for useful things, like accounting and this thing, but that is not math. The math is answering that question. And by answering that question is when we come up with these other useful things. And the other thing I'm saying that children ask these questions. So if you ask a child and the child is counting 1, 2, 3, which none of you are asked, they are going to eventually ask, where do you stop? Does it go on forever? And when it reaches forever, and I add another number, what happens? And if I keep on going that way, does it wrap around and come back the other round? Children will ask that question. Adults won't. And the adults who won't ask that question are the adults who have been educated. So you have the square root of 2, and you're saying that you could write it as a fraction, which means if I'm writing the square root of 2 as a fraction, if I could write out something and it stops, it means I can write it as a fraction because it stops. So I could eventually just take that and put it over the big tens, 100,000, wherever it is, and it's written as a fraction. So you're saying that I can write square root of 2 as a fraction, and I'm saying, well, I don't expect you to get this completely, but as I said, I want to give you questions for you to go home and look it up and to do like my friend Annalise said, to spark curiosity. So you have the square root of 2. I'm saying I can write it as a fraction, so I can write it as P line Q. I'm saying that can be done. So I'm assuming this can be done. So if P, and I'm doing it purposely, I didn't put this slide there to force you to do it in your head. So I'm writing P over Q equals square root of 2. If I want to kill the square root of 2, what do I need to do? I will need to square this side to get the 2. If I square this side, I have to square the other side. So I'm now going to get P squared over Q squared. So I have P squared over Q squared is 2. So which means that I would think about it hard enough, that 2 times Q squared has to be P squared. Which means that the P squared has to be equal to 2 of this Q squared. So I'm saying I can get a square, and I could get 2 smaller squares, and I could take those 2 squares and put in this square. That's what I'm saying I'm doing. So I'm now putting it together. So I'm taking the 2 yellow squares, and I'm putting it in the blue square, because I claim that that can be done. And with the sides that we have here, they're integers, because that's what we're saying we can do. A fraction is an integer at the top and an integer at the bottom. So we have a length P, because we're going to put them together. If you watch the size, obviously they'll overlap. So you have an overlap in the middle, and then you have the blue that shows in the middle. And I'm saying, but think about it hard enough, the orange must be the same size as the blue. Because you're taking the 2 squares and you're putting them together. I said the 2 of them are equal. So wherever overlap comes in the middle has to be the space that hasn't been covered yet. So I'm saying that the orange is the same as the blue. And then the other the harder part, the length of the blue has to be an integer. Because remember, I started off with the length of the blue, the whole entire blue, the whole entire length here is an integer, and the whole entire length is an integer. And from back, an integer minus an integer will always give you back an integer. We did it at the beginning. So that's the other lesson we're coming to. If you miss in your math education something, because when I went to the first part, the room was saying, and the listening audience, why are you going to these simple things? Obviously, we get that. But I guarantee you that half the room is stuck now. From the simple statement when I said that if I subtract this from this, that this here must be an integer. Because, and I remember when I said it, that if you subtract an integer from an integer, you get an integer. And everyone like, obviously, that is so obvious. So why are you stuck here? What's the conceptual leap that makes this difficult and saying that 5 minus 4 must give you 1? There's obviously a conceptual leap that in your mind that Samuel said it, and I believe him because he's a doctor, but I don't really see it. But it is obvious that the length of the blue and the length of the orange has to be an integer also. So we know, and it's also obvious that the orange must be the same size as the blue, which means that smaller blue and that smaller orange are the same thing. But you realize a problem. I could repeat this process again, and then what will happen? You're going to end up with the same result, and you can repeat it again forever. So there's no possible way that this statement could be true. And if this statement is not true, it means that this cannot be true. That the square root of 2 can be written in a finite set of numbers. It goes on forever. And that is the math. And that is the path that will excite somebody to try to understand why I should study mathematics and why this is important. And I'm making another statement that if you take your time and explain this to a primary school child, they'll get it. And be excited about it. And we'll look for a YouTube video on it. And we'll try to get paper and crayon and cut it out to see if it works. And we'll spend the entire lesson seeing that it's true. And we'll end up understanding fractions, shapes, subtraction, integers, all of these things in that. because they were actually trying to solve a math problem. They weren't trying to solve if you get 2 pencils at this thing. When we try to give real-world problems in our lesson, and we invent these real-world problems that don't exist in the real world. If you go to the shop and buy 3 pumpkins, nobody goes to the shop and buys 3 pumpkins. We don't do that. This is the math problem, and this is what math is, and I'm saying we do not teach this. We teach the application and the result of this, and then say that children can't do math, where we never taught them math. So that can't be done. There's another curious number that I was on my sheet, my number line. So you have a circle, and you measure the distance to the middle, and we call that the diameter, and you measure going around it, and you're going to get a number, and you divide them. And you try it with different numbers, and you divide them. And you're going to eventually realize you get the same number, and we call that number pi. And I'm making a statement again that you cannot write pi as a finite number. It goes on forever, 3.14159265, wherever 39, it doesn't stop. And then you're going to ask the question again, how do you show that? And I'm not going to show it. But the point is you eventually realize that there are numbers, and they've actually calculated this out to 1 trillion digits. 1 trillion. So they have calculated it out. And we know it doesn't end, and you could prove that it doesn't end. So there are numbers that you cannot write as decimals, so you realize you have a problem. And there's one final number that I'm going to go up to quickly, which relates to simple compound interest. So if you go to the bank and the bank is giving you 100% interest because they're kind, and you start off with $1 and you get 100% interest, at the end of the year you'll have $2. But suppose instead of waiting for the entire year, at the end of 6 months, they use half the year and they calculate the interest, and they calculate the interest on top of that, you're going to end up with 2.25. If they calculate it every quarter, you're going to end up with 2.44. If you make it shorter and shorter, you're going to eventually realize it goes to a specific number, 2.718, and that number is called E. And again, that number cannot be written in our real number system as a finite thing. So there are some special numbers that no matter what you do, they go on forever. To try to go to that as a homework, you're going to get that number E. So you end up with a number square root of 2. You end up with a number E, which comes from rate of change. You end up with a number pi, which comes from geometry. And none of those numbers, and that's the point I want to remember from all of this, you end up with pi from geometry. It cannot be written finitely. You end up with E from rates of change and calculus, if you do calculus, which cannot be written finitely. And you're like, okay, that's it. We have 0, natural numbers, whole numbers, negative numbers, integers, fractions. Fractions can be rational numbers. Those are the ones that can be written as a fraction. And then weird numbers like square root of 2, we're going to call them irrational numbers because they don't make any sense. And when we put everything together, you have real numbers, and we have everything. And the talk is over. But obviously not. Then you realize you have this problem. So you have x squared plus 1 equals 0. You subtract 1 from the left, subtract 1 from the right. You get x squared is minus 1. So therefore, x is the square root of minus 1. And then if you try to go back to your integers, you're going to realize if you multiply 2 positive numbers, you get a positive number. If you multiply 2 negative numbers, you get a positive number. So how can you take a square root of a number and get a negative number? So you end up with a problem now that you cannot solve using real numbers. So obviously you do what mathematicians do. You invent a number, and you call it I, and you say I is the square root of minus 1. And once you do that, you realize you can solve that because the answer is now I. So you say, so we started off, so this is the key now, we started off conceptually with matching our symbols to physical objects. And we keep extending it, and every time we match it back to a physical representation, and we keep extending it, and you reach a point where you have this. So then the obvious question is, what's the physical thing for this? How can you think about the square root of minus 1? And the way they did it is to say that when you go left and right, you have your real numbers, but if you go up and down, you have these numbers that we call imaginary numbers, complex numbers. So they're not on this line. You also realize something interesting when you add. If you add, you keep on going to the left. If you multiply, you're either going to the left or the right. So you invent this. And then there's a deep philosophical question that's being questioned. The numbers that we invent, the 1 and the 2, are they just our human representation of the physical thing, or do these numbers would have existed without us? So that's a question to answer. So you could have 5 apples, but what's 5? And is that any different from inventing I? And so now you ask, I now have my I, can I solve all equations now and don't have to invent any more numbers? And the answer to that question is yes. Once you invent this I, there's no equation you could write that you cannot solve, and it does not come back within the number system. So like we have finished with numbers, we are good. We have invented this weird square root of -1 called in I. Does it have any existence on its own? Is it just an abstract thing that we have invented to solve these things that have no real world things? And then I'm going to partly answer this. The rest you'll answer in a philosophy and theology class. This equation here, you don't have to know what it means, it's irrelevant. This equation here is the equation of all things small. So that's the equation of quantum mechanics. So any question you ask about something small, this equation will answer it to 13 decimal places. We will do that. Any question you ask, we will answer it. But you realize the equation as in the I. For this physical equation to work, you have to put in this mathematical thing that we invented called I, otherwise it does not work. To get physical results, the I must be there. It's going to disappear in the end, but it has to be there. And they have shown there's no way to rewrite this equation without the I. So then you ask a deeper question now. These numbers now that we invent that have no matching, what are they? Because it seems that they are physical processes that's following these mathematical formulas that we have invented. So we've come here. This picture is come from solving an equation that requires complex numbers and drawing these things, and you get this beautiful artwork, and that's for your homework to figure out how do you get it by solving the math. The math will give you this. And this is the most beautiful formula in maths, which again is your homework. Remember, and this is the key, we said the E is a number that has no end. It's 2.7182180, it goes on forever. We said the I we invented as the square root of -1. The pi come from geometry, which is just the circumference divided by the diameter, which is a real physical object. So there's something deeper in that I don't realize, it means that we have a circle, a diameter, and the length that goes around here, we have no way of ever writing down that circumference exactly. It's impossible. But if we combine them like this, the e to the I, we get the 1, which comes back from integers, because anything multiplied by 1 in the integers gives you back itself. Anything add to 0 in the integers gives you back itself. If I combine e to the I pi plus 1, I get 0. Combine a number that doesn't end, raise it to a number that doesn't end, with a number I've invented, add 1 to it, and I get 0. So there's a connection between geometry, calculus, number theory. They're connected. Anyway, Euler showed this in 17-something. So this is the full list of all our numbers, and we have completed all our numbers. And then you could ask the question, are there anything beyond complex numbers? They are, but they're not useful. You could always come back into complex numbers and solve all problems. So to wrap up, so we're doing math. You have a dot on a circle. I ask you how much area, parts, if I put 1 dot on a circle, how much parts is in that circle? And the answer is 1. There's 1 hole there. I put 2 dots on the circle, and I join the 2 dots to each other. How many parts do you have? You would have 2, as you can see. I now so you have 1, 2. I now put 3 dots on the circle. And I connect all the dots to each other, so each dot is connected to each other dot. You now have, if you count them, you have 4 parts. So you give the child the problem. You now put 4 dots on the circle and join all the dots to each other. So you have 1, 2, 4, and you're starting to see some kind of pattern. You count up the number of spaces you have. If you count that, you get 8. You now put 2, 3, 5 dots on the circle. You join every dot to each other dot, and you count up all the parts. You get 16. There's a pattern. So you're going 2, 4. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So I'm now going to put 6 dots on the circle, and I'm going to join all them, and I'm going to count the parts. And unless you know the answer, what do you think you'll get? You think you'll get 32 because it works for that, it works for that, it works for that, it works for that. It seems to be 2 squared. I have a pattern. I have done a couple of examples. Clearly, I'm going to get 32. If you do that, you're going to get 31. 31. You could try it any way you want. You're not getting 32. You're going to get 31. And there's a lesson to be learned here, something deep here. You could see, unless you prove a formula or something, 1 event and 2 events and 3 events happen is not a pattern. 4 events, 5 events, 6 events is not a pattern in maths. You have to show it. 1 billion events is not a pattern. There are people that propose relationship between numbers and you didn't find the error until the quadrillionth number when it failed. So you have to show it. So if you give this problem, you're going to get 32, and then you ask them to figure out why it's 32, and you involve a lot of complicated math, but it can be done, and you can get the formula which works. It's going to eventually work for 256 and fail for the in-between part, and then the question is, why does it fail? Which is the math question. Why is it not 32, and why does these go in multiples of 2 and then stop here? Why is that? So to show something in math, you can't just look at the patterns and say it goes on forever. You have to actually show it. There's a YouTube videos on it, which goes back to the question a child will ask. So I keep counting, and every time, who can say the biggest number? And you're going to say 5, the child is going to say 5 plus 1. You say 1 million, the child is going to say 1 million plus 1. You say 1 billion, the child is 1 billion plus 1. 1 million billion, the other child is going to say 1 million billion plus 1. Which asks the obvious question, when does it end? If you keep going, where do you go to? You're clearly going someplace, where do you go to? And we have this wonderful symbol called infinity. And there was a big argument, remember, there was a big physical argument, can you have something representing nothing? So you now have the reverse argument, can you have something representing everything? And there's some deep things in that I'm not getting into. But, so invent this thing called infinity, and we are counting. And I'm just going to do this quickly, just to force you to realize certain things. You can construct this object. So I can write a function graph, don't worry about it. I can do this line, the orange line, and I'll rotate it around like that. And I'm going to create this horn, which is called Gabriel horn. It's a 3D object, because I'm taking 1 over x, which means on the x-axis, I've skipped graph theory and all of that, on the x-axis and the y-axis, I'm plotting that, and then I'm starting from 1, and I'm going to get the shape. And then you're going to ask 2 questions. It goes on forever, so you're going to say, as you divide by a number, 1 divided by 2, 1 divided by 3 gets smaller and smaller and smaller and getting closer and closer to 0. And you're saying when it reaches infinity, it is 0. Because 1 divided by a very, very big number is 0. So the shape is going to pinch off someplace infinity out here. And you can pour liquid in it. There are tools, you could calculate the volume. It can be done within calculus, within 5 lines. You can work out the volume. You're going to get a finite number. That infinite shape holds a finite amount of substance. And then I'm going to ask another interesting question. What about the area, the surface area? Can I paint it? And I'm going to come up, again, it's a simple problem. Not simple, but it's a problem that can be done in 5 lines. And I'm going to come up with infinity. In other words, you can invent a shape that can hold a finite amount of liquid, but requires an infinite amount of substance to coat it. Now, think about that one. You also have this shape. So you start with a triangle, and you realize what they do. You take each side of the triangle, and you create another triangle. So I take this side, and I create another triangle, and then you repeat the process over and over, and you keep going, and you do it. I'm going to do it an infinite amount of time, and you get a shape at the end of that process. You can show clearly the area of that shape is finite. I can draw a circle around it, and it's clearly contained. It's finite. You can show, again, within 10 lines, that the perimeter, which is the distance around that shape, is infinite. So you could have an object that has an infinite perimeter, but a finite area, and it can be shown such that a grade 6 child can understand it, because it's simple, starting from there and then show how you do the perimeter and add it up, and you will get a finite number. So you could have a finite shape, the finite area, but the distance around it is infinite. So think about that one. Then this is the part I'm going to end. So you count up your real, and I want you to concentrate on this part, because this part is fun for me. You have your natural numbers from 0, and it goes up to infinity, and we can keep going, and we're going to come up to infinity. Now, you also have your real numbers point, and you're saying, everybody said that you could write out an infinite number of real numbers. You can write out an infinite number of natural numbers, and we have both infinities. What does that mean? So I'm starting with the natural numbers on the left, 0, 1, 2, 3, and I'm arbitrarily writing some real numbers, and I write to match them 1 to 1. So we're going back one step. I'm saying if I have a set of things here, let's call it A, and I have a set of things here, let's call it B, and I can show that I can match everything on this side exactly with everything on this side once they're the same size. If you want to dispute that, you're going to have problems. So if I have a set of two things, and I can match what's on this side exactly with what's on this side, so I match a pear to an apple, a dot to a dot, and nothing left over, they must be the same size. You accept that statement or you don't, but most people will accept that statement. If you don't, math collapses. So otherwise, you cannot define. How do you define? Remember, we started off by saying, I'm going back to the very beginning, that we're in a symbol called 1, and I've matched the symbol 1 with 1. I've matched the symbol 2 with 2, and we're saying they have the same size. If you don't accept that relationship, you can't do math. So I need to match. So I need to show I have an infinite set of natural numbers. I have an infinite set of real numbers, and I need to match them 1 to 1 to show what I'm talking about with infinity. I'm going to come to an interesting conclusion. The natural numbers we're saying go to infinity, so we're going to use all of them. So let's use up all the natural numbers, all infinite set of natural numbers, and we're going to match them to some real numbers on this side out here. I just random. Look at the red. So coming down the red, I'm picking the first number after the 0 for the first one. Well, then the other one, I'm picking the second one, then I'm picking the third one, then I'm picking them on the diagonal. Then I'm going to do something interesting. I'm going to change each of those numbers to something different. So I'll change the 2 to a 7, a 9 to a 4, 3 to the 6. And I'm telling you, and tell me if I'm wrong, that number there, 0.74, does not exist in that setup there. And why doesn't it exist? It can't be the first number because I've changed the first one. It can't be the second one because I've changed the second one. It can't be the third one. So this number here cannot exist in that setup there. But I started with an infinite set of natural numbers matching with them, and I've come up with a new number which is greater than the infinite set of integers. So I'm saying that some infinities are bigger than some. So when you count to infinity, you can count past it. to infinity and beyond. In mathematics, the art of asking questions is more valuable than solving problems. I thank you. Any questions, criticisms, comments?
Good evening, Mr. Speaker. A very thought-provoking presentation. So I am from the Montserrat Secondary School, and my question to you seems as though you're purporting that we should be doing concrete presentations still at the secondary school level. So can you expound on that?
It's two things I'm saying that we are claiming that the math that we are teaching the children is for them to use in the real world. That's what we say. They need to learn math because they're going to use it in the real world. And I'm saying we don't. The math that we teach, we do not use in the real world. We do not. There is no math beyond grade 6 that anybody uses unless they're engineer or scientists. None. By grade 6, you're learning addition, multiplication, percentage, everything. Everything you learn after that, and you do graphs and everything in grade 6, I've seen the syllabus. Everything you learn after that is for engineering and mathematics and specific fields. You're not using it. So if you're saying that's what we're doing, I'm saying we're not doing that. There's nothing wrong in doing what we're doing, but we have to accept that that's not, we're not training them for the real world. And I'm saying something different. When we teach music, we don't teach it the same way. So when you teach music, you don't say all the child is doing is scales, or all the child is doing is exercises and problems, a half note plus a half note, a whole, and you give them a whole set of exercises to do, and you give them a whole set of relationship between things and test them on that and say they know music. At some point, you're going to let them play a piece, even when they make a mistake. You're going to let them play it. And I'm saying at no point we let our children do mathematics, that we teach them tricks of how to do things. And I'm saying it doesn't work because the tricks are not transferable, so you learn the tricks will go to the other side. But if you have a half equals 6, a minus a half minus 6, and you try to go aside and carry across the minus sign, you're going to have a problem. It's not going to work. So we have to decide, that's a question the country and everybody have to answer, why are we doing it? If you're doing it to equip people for the real world, we're clearly not doing that. So you have to ask the question, why are we doing it? If you're doing it because it's intellectually curious and to drive curiosity and to drive problem solving, which is what we say. So we teach you to do problem solving and creative thinking and open-ended thinking and all these fancy words. Then that is not working either because you don't do these things. You don't do questions that the children ask about. We give sums and we give quadratic formulas and tell them the quadratic formula and tell them this is how to solve it and tell them this is how CXC is going to ask the question. When this question comes this way, answer it this way. When this question comes this way, answer it this way. If you learn enough of that and you're bright enough, you're going to pass. And then you're going to go 6th form and fail maths. So I'm just saying, if two things have to happen, we have dehumanized mathematics into a set of procedures that need to be followed, and it is cold, hard logic rules that are being bestowed upon us by God or whatever, and you just need to follow these rules and everything work out. And I'm saying something different. Mathematics is something we invented and it's a language that we have used to try to understand physical reality. We invented it. And we found out that it's useful to explain things that happen in the natural world. But math is not taught that way. It is taught as a set of rules to follow. It is not taught that this is a problem. How do you solve this problem? And in deeper, which is the one that we're very careful about. So you're teaching math and you know you're teaching this today. So you go home and you work out the problem, all of them, so you have the answers. And while you're home working out, you make a mistake, because you're going to make a mistake with all human beings, but you correct it at home, and you realize this method can't work, this is the best one. And you present the final best one on the board to the students, leading the child to believe that it was obvious how you got from here to here. No, it wasn't obvious to spend the whole night trying to figure it out. Let the child struggle with you. Ian, you're going to board and make a mistake, but that's how it works. You're going to make a mistake, and then you're going to figure out this method can't work. Let me try this one. Let me try this one, until you come up with a way to do it, because that's how the real world works. Where you give the idea, if you just follow these steps, which, since I'm clever, I'm telling you, you'll get the answer. It doesn't, nothing works like that in the real world. You're going to make a mistake and come back and fix it. And you're not going to spend 2 minutes on a question. And what happens with that, when I get a problem, and after 1 minute, 10 seconds, I can't figure it out. I can't do it because I'm not a maths person. If I get the similar question and I can't do it in 2 minutes, I'm going to tell myself, this was in a primary school book. Of course I can do it. And I'm going to sit down and spend the night and figure it out, even though it took me all night. But you who think that you're not a math person are going to stop after 10 seconds.
Interesting. Anyone else with the next question?
Good evening, everybody. I don't normally speak at these things. I sit and listen. But very interesting conversation. When I went to school, I hated math with a passion.
But you never taught it.
Hated math. And I think a part of it was the pressure of trying to understand everything perfectly. And if you made a mistake, well, there was no room for mistake. Because if you made a mistake, then there was a consequence to making a mistake. So you kind of associated making a mistake with math with a consequence. And so you hated going to math class because you didn't want to make a mistake, right? I became a teacher, and math became the favorite thing that I like to teach, which was surprising to me. I prefer to teach it than I did language, English, which was one of my favorites in school. But I became excited about it because it forced me to become more creative if I wanted the children to understand. And so, like you said, I had to try and figure out a lot of things and try to figure out creative ways to try to get them to understand what was happening. Now, you said a few interesting things. I have a lot of notes. Critical thinking and developing. And I think you hit the nail on the head when you said that we try to give the children shortcuts. As teachers, we really try. You want to ensure that they get it, and so you try to make it easy by coming up with something that you think will make it easier for them to get to where you want them to get. Yes. And so you try to come up with all of these creative, easy ways, and then again, when they get to something that doesn't fit into the pattern and they're stuck, then you realize that really they didn't understand the concept. I think the first time not the first time, I think up till now, I do tutoring still, and even with the timetables, we teach the children to learn the timetables by rote. So they go home and they learn 1 times 2 is 2, 2 times 2 is 4, then they get to 12 times 2 is 24, and they stop there. And if you give them something in the 2 times table that is not written down at the back of the book, they have a hard time trying to figure it out. Although you're saying, listen, look at, there's a pattern. Right. You tell them there's a pattern. You just keep adding, it's repeated addition. But somehow that jump in trying to understand how we got there in the first place. And I think we don't spend enough time with that part of math, as you said. As long as they can repeat, because you asked them to repeat the timetables up to 12. And they stay up to 12 and you think, okay, they've got the concept. But you give them something that takes them down to 100 and something as an answer. It's really difficult to make that leap. And so one thing that I've learned is that we need to take the time to teach them the process. The process is important. It's not the answer at the end. And I don't think sometimes we get that as teachers. I'm not an abstract person at all. I'm one of those people that have to use my hands. Even when I speak, you'll notice that my hands are always moving. I have to manipulate things and do it for me to understand. How do we integrate that and the different learning styles of the students in presenting some of these concepts? Because I was sitting there, I was trying to follow you, and you were right. By the time you got to the more advanced parts of the presentation, I was like, okay, I'm lost. I have no clue what he's talking about. He'll have to sit me down and have me do something to get me to follow along. And so we have students like that as well within our classrooms. I taught an exam class in primary school. We are given a set of topics that must be covered by a certain amount of time, because I don't write the exam is written and given to me to present to the children. Yes? And so you're kind of forced to try to cover the content of the syllabus so that the children can meet this deadline that we have said that they need to meet. They need to be here at this point, and so they need to get it. And so you kind of rush through. Like you say, you don't have the time for them to sit there for an hour to try to figure out this one thing that they don't understand. You try to rush over and say, you know what? This is what you have to do. Just move it over there. And if you see, and you're right. If you see this in the test, this is how you work out that. You understand? How do we change that? That's a conundrum as teachers that you face. Like, how do you prepare the children to meet these standards that we say they have to meet within the time frame that we are given?
But I'm saying what you're doing now doesn't work.
It doesn't.
Because no, I'm saying that we're doing, you have to do this work, or you have to meet the syllabus, and you have to do these things. So we have to do these things for the children get it. But they fail, so they didn't get it. The data shows that half of our children fail, which means that idea that if you rush them through and give them the idea, you have now done something and they've got it. But they haven't, because when you give them the exam to answer it, half of them, I remember we consider pass grade 3, which is less than 50%. So when we say children pass, it means that half of the material they don't understand, and more than half of the population can't. So I'm saying what you're doing does not work. So we do it and say, oh, well, we have to do it because it's what's work. But it does not.
Okay, so that's the question. That's the question that I posed. This is the system. How do we change the system? Because it's the system that we have. How do we change the system to accommodate this type of teaching of math? I mean, you don't have to answer the question. It's rhetorical. I'm
going to wait for Howard to nod it. Wait for Howard here to nod his head, because he does music.
It's rhetorical.
If you're teaching music and you give the child Beethoven Ode to Joy, and you tell them play it, you can give them tricks and tell them when you play this, put this finger here. And at the end, they're going to know enough that it sounds about right. And if you grade them, they're going to get 50%, and they're going to get a grade 3, and they're going to pass. And you're going to try that. Or you could go back and ensure that they understand music theory, that they understand music scale, and teach them from there. And I'm telling you that the child that you do that with is going to advance faster than the child you try to rush through. So you feel that you're slowing them down. I'm saying if they get the base, if you truly understood what I said about integers and going to the left and go to the right, and you truly understand that's what we are doing, the other stuff I did is of the same conceptual difficulty. And so hold on. When I used to teach sixth form math, the first thing I used to look at all them coming with the grade ones, I tell them 1 over A plus 1 over B. And they stopped because someone came and they don't remember. And they said I had. So I said, okay, 1 over 2 plus 1 over 3. And they work it out. They say LCM is 6, 2 into 6 is 3, 3 plus 2, 5 over 6. But say there's no way you could do 1 over 2 plus 1 over 3 equal 5 over 6, and you cannot do 1 over A plus 1 over B is equal to A plus B over AB. It means you didn't understand 1 over 2 plus 1 over 3. It means somebody told you to write a 6, and somebody told you 2 into 6 is that. But if you understood that you have 1 over 2, 1 over 3, and what you put below there is 2 times 3, you have 1 over A, 1 over B, so what you put down there is A times B, so you have now matched it. You have now said 2 into 2 times 3 less but the 3, so A into A times B less but the B, plus the A plus the 3. You would have matched it back. So when I get the problems, even when I was doing my advanced stuff, I'm matching it back to the stuff I did in fractions. I'm not saying I'm clever and I could do abstract thinking. There's no abstract thinkers. I would literally write down the fraction, write down the complicated thing that I have, and match it back to the rules I followed here to get the answer. So if you understood that fraction clearly, that's what you're doing. You're trying to get equal parts to get everything shared equally, you would do the algebra. So if you do that in primary school properly, the algebra is going to finish in one term.
Okay, so which brings me to the end of my notes here, which I wrote that it is important normally in a lot of the mistakes or a lot of the bad math, for lack of a better word, occurs normally in the foundational stages, which is what I think you've pinpointed here, that if we don't allow the children to learn the math, which is the basics for them to build up, it doesn't matter what you do as they go up, it'll crumble. And so, again, I go back to, because we do have a system, and this is not an excuse for anybody, but we do have a system by which you are graded, not just the students, but the teachers, the schools. You have to tick off these, Teacher Catherine is right here. You have to tick these boxes that says you're behind, or, and you get that you're behind, you need to move forward, you can't spend any more time, you need to go forward. How do we, again, it's a rhetorical question, how do we reset, especially the foundational syllabus, so that we can spend more time to ensure that the foundation is strong, so that there's something to build on as they go further up?
So I'm going to answer it in two ways. Well, one of them is I'm just going to give an observation. I won't answer. I'll just give an observation and enjoy a conclusion. Across all systems, Montserrat, Antigua, Barbados, all of them, we place the, better is a bad word, but the teachers that have degrees in mathematics, we place them at the secondary school. And the other ones that don't, we place them at the primary school. We also pay the teachers at the secondary school more than we pay the teachers at the primary school. Arguing, so I know this isn't going to cause controversy, it's fine, arguing that the foundation level is the most important part, but we are going to put the resources flipped. And complain at the end that the house crumbled because you put the roofmen there and you put the laborers below, and you don't understand. But we do it. It's not just a Montserrat problem, it is what we do. We say that it's his primary school maths, therefore, you went to secondary school, you pass it, of course you could add, you could teach a child you love children, you're friendly, you could teach the child in math, we don't see the issue, and we flip it. And then when the child hits secondary school, they complain, but so derive from that what you like. But that is one thing that we do. And the rules, as I said, Teacher Catherine, know the rules that we use to evaluate these things, we set them. They weren't given to us. We set them. So take what I want, is we set these rules. So remember that one too. And is we decide as CARICOM and as OECS and as a country what we put into our syllabus. It wasn't given to us. Is we decide these things. And we say we do experiments. So we had a system in the school where we move everybody through. And we had the results at the end, right? Then we invented a set system. We say, you know what? Children operate at different levels for maths and English, so let's put them in sets. And we split out the children in first form into set 1, set 2, and set 3, and we were running this experiment for years. But you're doing science and you're doing mathematics. So the obvious question you have to ask, if I look at data before sets and the data after sets, has there been an improvement in maths? I've never heard a question asked. So you have spent a whole reform and you have done something. You have the data from before because we have the results. And you have the current data, you need to compare them and see if, and I'm telling you that there's no difference. There's none. You're not, your CXC marks across the region have not moved. So clearly, you tried it, it didn't work. You have to try something else. I'll leave it for that you to answer.
I have some real-world applications to deal with. I really have to go. But thank you for the presentation. You leave me more confused, I suppose, than half of the rest of the room.
So I did my job.
You did your job. You have to ask me questions. And the other thing for me is that you need these things in the morning when our brains are fresh, and that's at the end of the day. So something for you to consider. But in the real world application, how do you encourage things like networking, collaborations, understanding, especially in the world? That's how things actually work. You need your team of people to help you through. So in this whole system of testing, you have to have your own. How do you, address that issue in our school systems?
Right, and that's the other thing, because we claim, again, it's a claim, that we invent our school system to prepare people for the real world. There's no real world office where you're going to and your boss says, this is the work, you do that, you do that, you do that, and don't talk to one another. It does not happen in the real world whatsoever. It's an artificial creation of school. You will be told you're going in a group and you all are working together to get things done. And even if you go to university labs with physics and mathematics, there's no one mathematician, physicist working on a problem. It's a team of people working on it. So again, it's a question that we have to answer. It's a deeper question than maths. What's the purpose of school, which is part 2, which we'll do after election. But there's a question that needs to be answered, and you're right with that. So we said that we do these things in the write-up that we do, but the actual practice does not match it, because that's not the real world. And then to show you how people mistake the real world for maths, because I remember I was teaching 5th form, and we were doing principal rate, what they call it, simple interest. And I gave the problem, you have this money in the bank, interest is that, after 5 years, how much money will you have? And the child brought the book to me, I watched it, I said, your answer is wrong, I gave him back. Like, sir, there's no way you could know the answer is wrong, you didn't check it yet. I'm like, I don't need to check it. The answer you start with is less than, the answer you have is less than the answer you start with, and it has to be more your answer is wrong. The child is insisting it can't be wrong because they put it in the formula, and that's what you got. But you would never do that in the real world. He would have never gone to the bank. The bank told him he got interest and he got less money and said that he's correct. So why, when you enter academic system, why do your brain shut off and you start to think in a completely different way? The answer is wrong. I don't need to check it. You made a mistake. Go find it. Why have I gone to your calculation? But I'm not saying you would never do it. So sometimes we say, oh, we're not a math person, wherever it is that we claim we not are. Of course you are, because if you go to the bank, you will never, ever make that mistake, but you'll make it in an exam. But you will not make it when you go to the bank.
Yeah, thank you. Good evening, sir.
Good evening.
I wanted to support the fine lady's assertion that the entire system of teaching and learning has to be revamped and revisited. And part of the answer you gave, sorry? Yeah, part of the explanation you gave, I think, supplies the answer, part of the answer to her query. Because if we're going to be arguing, as we have been doing for years, that the primary school is where the critical infrastructure must be laid, so to speak. But at the same time, we are taking those who are presumed to be the better equipped and placing them elsewhere. Yeah. That's an upside-down, inside-out, reverse kind of system. I have long concluded that the tests that we give to students, and including those at CXC, they're not designed to test what the students have learned, but to see how well they remember what the teachers taught. And there's a fundamental flaw in that. It means we need to de-school what we're doing at the moment. But I wanted to ask you, sir, and it's a follow-on to what the Honourable Minister asked a while ago. To what extent can these advanced mathematical principles be used to solve some, if not or many, of these critical problems that afflict mankind?
I'll come to the second one. The first one first. The one with testing. So you're playing basketball and you invite a coach to look at the teams playing to see whether they should go to the college. You are not going to sit down with children and say you are set shoot 10 free throws, then you shoot some 3-pointers, then do some passing, assign a grade to each, and then see, okay, you shoot 5 free throws, this amount of points you get for this question. You shoot this amount in 3-pointers, is the points you get for that question. The passing is amount of points, and then pick the person who gets the highest and say, that's the person I'm going to pick for my university. You will never, ever do that. You're going to watch them play basketball. And you're going to pick them from playing the basketball. Because somebody could go out there and very good at shooting, but too short to play basketball, the defense is going to kill them. So you're going to actually, but it's what we do. So you have to test. I'm not saying you have to test, you have to test because you're teaching something. I need somewhere to decipher if what I'm doing is working. But if you go to the basketball example, you would not give questions like that. You would give them a game to play to determine if they're qualified to come to your school. But if you're trying to determine should you come to do physics, you're going to give them a test. And in the Caribbean, we're going to pass it because by the time we reach that level, we become very good at taking tests. The techniques in taking tests. You become very good at taking tests. And us Caribbean people are going to do very well. And we're going to send our children to the UK and we're going to claim that they're doing very well. And they're going to hit grad school and fail. And then to the second part, which I'm going to pretend I forget. There's a deeper question because you come up with these complicated mathematical things, and I did number theory on purpose because it's the simplest one that we do in numbers. But you come up with things like calculus and differential geometry and statistics and all these complicated mathematical structures. And what you eventually find out is that these mathematical structures have a physical realization. So if you do quantum mechanics, it's a complete linear algebra system on a Hermitian Hilbert space. It doesn't matter what the word means, but it's a mathematical structure, and it's what describes electrons. You come up with Euclidean geometry, which is normal geometry we know on a flat space with triangles and Pythagoras, but there's a geometry of curved space, which is called Riemann geometry with some complicated mathematics, is what describes gravity. So you're going to realize you come up with this complicated, you come up with group theory about how things rotate and how things mix with each other with symmetries, and you realize it describes quarks and gluons and protons in an atom. So you're going to come up with these complicated mathematical structures that you just did for fun, and then some physicist is going to discover there's a physical realization of that, which asks a deep philosophical question. Are they the same? Fundamentally, what we are looking at, is it math? Because you can use math to describe physical reality to extraordinary precision. Why is that? Is it a coincidence or is there something deeper? Why is that issue? And you can come up with all these wonderful mathematical structures that is just math, and then some physicist is going to discover, if we use it, we get the answer to this question. Exactly. Not partially, exactly. We are now at the stage that every experiment we do matches what we have written. Everyone.
Good evening, everyone.
Good evening.
All right. My name is, I'm identifying myself so that when I'm finished, I am Deanne Whiskey John, and I am the, I have a long name, Advanced Skills Teacher Mentor for the primary schools.
See, she'll fix the
for
problems.
math. Yes. So a few things that I think the public, because I'm sure everyone is tuning in, should hear. One is that Montserrat has a new math curriculum for the primary school. And one of the things that I am responsible for ensuring it's implemented, and one of the things that we would have done is that all 3 primary schools across grades, we would have met. We got the curriculum, but we met. So grade 1, we had a meeting and we discussed and we looked at all that was supposed to be taught in the curriculum, and we decided based on what happens in Montserrat, because that's another thing persons need to take into consideration, how the term flows, contact hours.
Yes.
It's one thing to talk about content and even the innovative approaches that we want to use and we want to have teachers use in the classroom. Time is also of essence for them. And so we have to marry the two. So we got together and we did do that. So we were networking. All 3 schools are working together across. So they're supposed to be doing the same thing. In terms of the strategies, they are trying to do their best because, as you would have said, they may not have their degrees, but they are open. So this is where I'm putting the plug that perhaps some sort of professional development can be put in place for them so that the teachers who are there, they're willing, that they can gain stronger grip of the concepts. They don't have to do degrees, in my mind, but I think that they need additional professional development sponsored by the government, and perhaps as soon as you can, so that we can have an effective rollout, because we're piloting. And I would say that all that you have done here, I have seen teachers in the classroom who are doing their very best. They're creating the resources, they're doing the research, they're doing the play style. But that is not something that, so for example, we don't really have all the formal resources, but we're using all local resources. They are innovative and they're creative. And I want to put in a plug to say that most of what you have spoken about, we have begun to do that. So I think that Montserrat is uniquely poised, because the attainment test is not something that comes from CXC. We craft it here, and based on what is happening with the 3 schools networking, we have room to craft that attainment test to do all that you desire. All we would require is the full support of the ministry in terms of ensuring that the teachers, where there are gaps in terms of knowledge, that it is closed and that they are given that full support, and the other physical resources that they may ask for. Because we haven't asked for anything actually as yet. We're using all the local things and trying our best to deliver in a creative fashion. So I can answer the question, do we teach math at the primary schools? And I will say that we are getting there. Yeah. On a scale of 1 to 5, I would say that the teachers are at the 2 level, because we're focusing on developing the concepts, conceptual development, and because it's a journey, I would say that we are getting there. Yeah. We are not totally lost. And I think that, because I've taught in different Caribbean countries, I think that we are doing pretty well. We're progressing nicely, and we would appreciate if you would come, share some of your ideas across the 3 schools, because I have been trying to encourage the teachers to stop working in silos. It doesn't work out. And we have stronger teachers in different schools, and so they work together, and I'm hoping that we will all do the same exams, and we will, because they have to write some sort of exams at some point in time, but we're also focusing on the creativity and getting the children, more importantly, to love math, right? The emphasis is not necessarily the attainment exam, but getting that interest and that curiosity embedded in all the children. So when they get higher, whether we decide to let them select math, and all of them don't have to do math, but at least they'll be able to function in society, all right? So that is the primary school level. So we're not all lost. Unfortunately, I am defending Montserrat. I am saying that I think we are beginning to teach math. Yeah?
And to answer, instead I was saying all lost, and I'm saying to get things done, we live in a democratic society, is how it works.
Yes.
The public has to be on board.
Yes.
And the teachers have to be on board.
Yes.
So it requires, and the government has to be on board.
Correct.
So it requires people like me,
yes,
saying these things to the public.
Yes.
To get them on board to help you.
Correct. Thank you. Because we have a framework, yes, and it is so. We have a framework. So right now we're working. I mean, well, the government did employ me, and so that's a good start. But we also need, and the teachers, I think even if you visited the schools, you will see the sense of excitement. Because you see, people feel that it's, even if you have a math degree, it doesn't mean you can teach math. All right? You need a combination of things. You need the pedagogical skills. You need the knowledge of the math. You need the love of children. It's a unique recipe. And so the teachers that you have, they are ready, they are willing, they have the willingness, and they have been doing it for a while. So if we come together, I think by, let's say, 2025, when I'm ready to leave, we should be well on our way, because right now we're focusing on conceptual development. And they're doing, as I say to them, it's concrete, then pictorial, then abstract. No concepts are to be laid in the abstract form. So if I were to mark your presentation today, you would not pass. No concrete. So just to say, I am emphasizing that because we recognize, just as Ms. pointed out, the children learn differently, and they really want, you know, you really want them to love math, right? Because they have to use it in their lives. And it will hinder them if they want to go further. Yeah. They need it, yes? So thank you.
Yeah. And then to your point, if you love something, you spend more time on it.
Yeah, so I support what Ms. said just now, but I'm going to talk concerning Montserrat Secondary School because I think that there should be a follow through from what is happening in the primary school to the secondary school. And I've been working at Montserrat Secondary School for about 8 years, and I'm not impressed with the resources that we are given at our disposal in terms of teaching of mathematics. So firstly, you'll find that even the mathematics classroom is not conducive to teaching the subject, and we struggle a lot in terms of the physical resources to execute the teaching of mathematics. And I'm thinking if you want the teachers to be enthusiastic in teaching mathematics properly, to execute, helping the children with the conceptual learning of mathematics and the procedural learning of mathematics, we should be properly equipped. The physical classroom space should be inviting to the teacher, to the students, and we should be given resources in helping us to execute our teaching and learning thing. And I think at the secondary school that we have been shortchanged with that regards. And I think more attention should be given to trying to source proper resources for mathematics in the classrooms at Montserrat Secondary School.
That's it.
Are there any other questions for the minister?
Good evening, everyone. No questions, just an intervention based on observation over the years. Some years ago, we had some academics participating in a storytelling conference, and one presentation was about using storytelling.
Stand a little closer to the mic, please.
One presentation was about teaching mathematics using storytelling. And subsequently, I tried to interest the ministry in getting teachers in the primary school trained to use storytelling to get mathematical concepts across. There was a little interest. The other concern that I have is with the remark that was made just a while ago about putting the resources in the primary school. I think the resources also need to be placed in the early childhood setting, because that's when, in the early years, children are learning, you know, at a rapid rate. And if you're not optimizing that opportunity, you know, we are setting them up for failure later on. Thank you.
Anyone else with something to add?
Good evening. Dr. Samuel, why are you grinning so much?
I was trying to go to my desk out there.
You're going to go there shortly. Thank you for a very enlightening presentation. I prefer language to maths, though I have not failed maths. I kind of think you got me lost when you got into the highly sophisticated maths. Nonetheless, for the most part, the conversation this evening has been useful. I teach part-time, but I prefer language, right? Now, you spoke about all the different ways that maths is to be taught. It's to be taught at the foundation levels, and it's about the concept and the what have you not. I agree, because even as big as I am, I can remember the things I learned way back then, and even how to, the teacher that you're supposed to subtract from left to right, now I can actually do it the other way and add the other way and so forth, because I understood the basics. My question is, in as much as you've given us a lot to think about with maths itself, we have to accept that there is a challenge across the Caribbean, but we have to pinpoint it to Montserrat and the fact that we really have a problem. The results from maths have not been encouraging over the years. How do we arrest that? What is it that we are going to be putting in place? In the same vein, I totally support the notion that you need to have people teaching maths in the lower years who love maths, who understand, because I will tell you this, my degree is in a foreign language, and I had to do language and literature. But if you ask me to teach literature now, I will respectfully decline. I do not love literature. I run away from it. I would be the first person to abscond if you're looking for me. I don't love it. But I understand the utility of it for critical thinking and writing and all that good stuff. But I don't love it, so I can't teach it. How do we get people to teach mathematics who genuinely understand these concepts and how to teach it? That's the question. Because we have a spiraling crisis, for want of a better word. In the same vein, how do we fix this thing where our public service is asking people to enter with 3 subjects to include maths and English, when the majority of people, as the statistics is showing, are not passing maths? And you have rightly said that, yes, grade 3s are passed, but that represents less than 50%, right? Is there some way that we can fix the system so that we actually test people who want to join the public service on their aptitude for what we need? Unless you're going to be a doctor or an architect or an engineer, you don't need that kind of maths. You've said it. I agree. So then how do we fix this thing? Because I find it is disadvantageous when we want to employ persons and we tell them that we can't appoint them because they don't have maths. I feel that they don't have maths, but if they have English, we're not paying the kind of credence to that, and I think you need more English than maths for general entry into the public service. So, in long and short and in summary, great presentation, but you and the others who set policy have a lot of work to do to fix what is really an obvious crisis. Thank you.
Thank you. I'm supposed to answer? Let's skip the second part. The first, I said something on the first because it's important, because so every time we have this presentation, we automatically switch to the school, is what we do. We automatically put the solution, that is solution to societal problems, lie with the school. And if we start with that premise, you're not going to get the answer, because we're saying it's societal problems, which means the societal solutions. If you start off in a household and you're 5 years old and you go home to mommy and daddy and you bring the subject from kindergarten and you bring the work and you try to ask them to help you, and they make the statement, I was never good at math, I don't like math, there's nothing the school could do. You have created a problem. You've already told the child it is okay, because it is, you can go to a party, and if you go to a party and you said, I've never read a book, or I can't read, you're looked at with shame and you have to be done or something. If you go to a party and say, I never like math and I never like physics, you're giving praise. You're going to hear me too. You have constructed a society that has said that this is not important and it is okay to make jokes about it. So the school is starting behind. I don't know how the school is going to fix that. And we have also constructed a society because we came out of slavery. And we came out of a system of field slaves and house slaves. And we came out of a system where the house slaves were educated and for whoever looked down on the field slaves, we call the field slaves, to look down, to don't see intellectual ability as something to be looked as positive. So we have insults in our society that say, he think he bright. So telling somebody in our society that they're intelligent and they could do work is an insult. And we need to think about the societal implications of stamina. And the Asians don't do it because it's an insult to go to school and get an A and not to get a B. But in our society, if you get the B and you didn't get the C, at least you pass, because I never could do it, and you do better than me, and 5 times me try, and you finally pass, you're doing good. You have to say that this, if you start with that from a societal level, the school is going to try all it like. It's not working. I have you from 8 to 2, and you have them whole weekend, and you have them the whole afternoon, and if you're not having that conversation, you're going to have problems. So that's the first thing. And second one, as the society has to decide, and I'm saying it, and it's going to be controversial, we have no problem paying lawyers, and we have no problem paying engineers, and we have no problem paying deputy commissioners, but we have a problem paying teachers, and it has to get fixed.
I don't want to take too much time, but you said something there that I wanted to put a plug for, and that is I want to implore all the fathers. Because men, it's a gender thing. They tend to gravitate more to the math, and I know St. Augustine would have done something where they asked their fathers to get on board with the math. And it is something that we need. This is where we really need to call on the men. You know, you have your children, encourage them, take them to work with you, because men, their professions, generally, it tends to gear towards the math. And men are not afraid to, you know, like I saw a video recently of a parent asking a child to drive a tractor on Facebook. And I was saying he was very firm with her. And I was saying, you know, if that was a mother, she'd say, no, the child can't do that, and so forth. And it would have, you know, the father would be firm. And I think I can put a plug here. I think that would go a long way to removing the fear of math in the society. If the men came forward, if the dads came forward. I'm not saying that women don't do math, but I'm saying that a lot of the male professions, they use the math more, and therefore you can get more of the males on board and more of the fathers on board. I'm putting a plug for that, because we usually at meetings, you only see the mothers. Yes?
So just a quick pause. We had a question online, but I believe it was asked along the way before. And they were asking, as an educator of teachers, I often see my teachers using procedures, the same tricks as you mentioned, as opposed to the fundamental concepts. When we suggest to them to teach conceptually, they often complain that those methods take too long. How do we inspire them to actually teach mathematics rather than simply prepare the students for the next exam? I believe that was something that was asked along the way.
But people are going to do what they're rewarded for. If I'm a teacher and rewarding me for passes, I'm going to give you passes. So the people are not foolish. People are going to respond to what you tell them to do. If my PDA says I must get 60% passes, tell yourself at the end of the year I will figure out how to get the 60% passes, whether or not the children. So part of the fixing is to change the incentive on the other end, and the teachers will adapt to it. And you can't blame the teachers for doing what you tell them to do and what you pay them to do.
I just want to share a practical experience I had. My nieces and nephews were over for the weekend, and we decided to make a cake. And I said to them, double the recipe. They were like 7, 6, 5, and they figured it out. Right. I left them to work it out, and they worked it out. We had 2 perfect cakes. So teaching math doesn't need us to say that we're teaching math. You know, you're introducing it in a practical way. And I remember a friend of mine in the UK, her son had an exercise to do at home. He had to mark off a square meter in the garden and observe it over a week, the ant life, insect life within that square, and so on. And it made me realize I don't have a physical understanding of distances. Like somebody would say, walk down the road 50 meters. I have no idea what that is. But if you start with some exercise like that, a child actually ends up understanding what 50 meters down the road means.
And then my final comment before I go, it's getting late. And that is the point I was trying to prove with the other one, because I have children, and it's so nice to blame the school. But if I'm going up the steps, I'm counting them. 1, 2, 3, 4, 5. Then they're going to count with you. Then you're going down the steps, you're going to count 2, 4, 6. What's the next one? You have to do things like that in your normal conversation. It's not something outside of your normal routine. It is just part of your conversation. You're driving and you say a number, what's that number? 246. And I pass another one, 23. What happens when you put the two cars together? It's just a normal part of your conversation, or something extra you add on. Just like how you talk about music or you talk about culture. You don't say you're talking about calypso because of a music exam, you talk about calypso because you're talking about calypso. These things have to become integrated into normal. And on that note, I bid you farewell.
What an interesting session we've had here this evening. So now I am delighted to give the vote of thanks for this evening's event. So ladies and gentlemen, on behalf of the Ministry of Communication, Works, Labor and Energy, the Montserrat Volcano Observatory, the Ministry of Education, Youth Affairs and Sports, I extend our heartfelt gratitude to each and every one of you who graced us here with your presence today. Your participation has not only honored us, but also contributed significantly to the success of this evening's event. First and foremost, I would like to express our deepest appreciation to our distinguished guests, the Governor and her husband, our honorable ministers, the Speaker, our permanent secretaries, our directors, educators, and STEM professionals. Your esteemed presence has elevated the significance of this occasion and added immense value to our discussion. A special thank you to our presenter this afternoon, none other than the Honourable Samuel Joseph. Your insightful presentation on the details of mathematics have left us with much to ponder and has undoubtedly enriched our understanding of the subject. Your expertise and knowledge is truly commendable. I extend my gratitude to each and every attendee who graced this evening's Math Talk with their presence. Your active participation and engagement has made this event truly memorable, and without your support, this gathering would not have been possible. Your commitment to educational discourse is deeply appreciated and serves as a testament to our collective dedication to fostering intellectual growth and exchange. We're immensely grateful to our dedicated team of organizers and volunteers who work tirelessly behind the scenes to ensure the smooth execution of every aspect of this event. Your hard work, dedication, and attention to detail have not gone unnoticed, and the success of today's proceedings is due to your unwavering commitment. I would also like to extend our thanks to Ms. Anna Johnson for our warm welcome today, Reverend Tolly Allen for leading us in prayer, Ms. Shal Chapin, your moderator, myself, hi. The ICT unit within the MCWLE staff, Ms. Tiffany Williams from the MVO staff, Events M&I for their impeccable decor, as you can see, and the Montserrat Cultural Center for graciously hosting this event. allowing us to host this event. Last but certainly not least, I extend our gratitude to the technical team that you see there sitting in the back for the evening, the Government Information Unit, and iTech Montserrat. Your assistance ensured the seamless execution of the technical aspects of this event, and we are truly grateful for your support. As we reflect on the success of today's proceedings, let us carry forward the spirit of collaboration and inspiration. Together, we can continue to foster meaningful dialogue and a positive impact in our communities. Once again, let me say thank you. Thank you to everyone who played a role in making this evening's event such a resounding success. Right? Have a safe journey on your way home, and again, thank you for being here this evening. Oh, yes. So today was our second activity in our STEM week, and this is our first time ever having the week. It's our inaugural week of activities. Today's Tuesday. Tomorrow, Wednesday, we have our school visits. We'll be visiting the third formers at the Montserrat Secondary School. We'll have various professionals in the field of STEM going there around 10 a.m. They're about to talk to the students and inspire them in the various subject areas of STEM. Those who already have an interest in it, those who have probably made up their minds as to what subjects they want to take for CXC. So we have that talk with them tomorrow, as the third form is the form in which they choose their subjects. And on Thursday, we have Girls in ICT Day. This is celebrated internationally. We'll be taking the grateful girls on field trips, and they'll be speaking to leaders, women as leaders in various areas of volcanology, communication, and energy. So that will be an exciting day for them. And on Friday, we have our big shebang. We have our STEM fair and exhibition. Our exhibition will feature various government organizations putting on exhibits for the general public to come and see. And we also have our fair, and as we've been advertising, our fair is open to each and every one to come and participate. You can bring an experiment, bring a project. It just has to be somewhere within our field of STEM, science, technology, or engineering, or math, on any of those topics, and you can bring an experiment, bring a project, and have the opportunity to win yourself a prize on Friday. But you have to register by tomorrow. And again, so to close out, thank you to everyone. Thank you for coming, and a safe journey home.